Today we're going to look at interpreting gas chromatography data, and I'm going to do this in the context of an experiment, experiment 21 that we're doing, where we're looking at butanol, 1-butanol, and under acidic conditions looking at a competition between these two nucleophiles. So they're both good nucleophiles, so we're going to get both products, but we want to know what's the major product going to be. Is it going to be more of this bromide or the chloride product? So before you move on, I want to make sure that you have a prediction and you have a reason for that. So you could either talk about the basicity or the nucleophilicity, talk about the substrate being primary as opposed to secondary, tertiary, and putting all that together, is there a reason why you think one of these might be major, and which one do you think it would be? And I want you to do that for all three of the alcohols that we did as a class, which includes the 2-butanol as well as the tert-butanol. So for these as well, you're going to get a product distribution of some kind with a bromide and a chloride. And I want to make sure that you explain your answer. So if you pick, let's say you say the bromide is major. I want to know, what are you basing that on? And it's totally fine if you're wrong, okay? So the point is that you're thinking about the concepts and then you're going to verify this by the experiment. So pause it here. If you don't have that all done, I don't want you to have looked at the results yet. Okay guys, so here are the results, and this is a gas chromatogram. I can't fit it all on one page, but take a look here. We have one peak coming out here at 2.6 minutes and the other peak at 2.8 minutes or so, okay? And I did I ran some standards. That means I have a bottle of this and I have a bottle of this, and I ran them not from the experiment, but just to see where the molecules come out. And their retention times come out right about here. So the chloride, when I ran that by itself, it came out here. The bromide came out around here, and then I ran them together as well, and they showed that they came out at that region. So I'm pretty sure this is the bromide and that's the chloride by running those standards under the same GC conditions. So now that I have the two peaks, let's take a look at them. You can see they're different heights, but more importantly, we base the percentage of each one based on the area, so the integration or the area under the curve. Now it's a little bit difficult to use that graph because it doesn't fit on one page, so let me redraw it here. So we saw something like this. We had one peak here and another peak here, all right? And this is what we call the retention time, how long it took the molecules to elute off the column, and then this is sort of the intensity. So I had the chloride product coming out earlier because the retention times are based on boiling point, and the chloride is going to be lighter and so has a lower boiling point than the bromide. So here's the chloride product. And then the bromide product was this one here. So I may have mentioned in class different ways that we can determine the area without calculus. We could figure out the area based on triangulation method. So if we pretended these were triangles, we could do 1/2 base times height calculations. You could also cut out from the piece of paper. You could cut this peak out and cut this peak out and weigh them. So you can get the area ratios that way. Luckily for us, we have the computer do that. So, but it still involves the calculations. So let me show you that. So to get the area, I did a printout of that. So you can print out the integrations, and I circled 8 and 9. 8 and 9 are the peaks that we're looking at, 2.6 and 2.8 minutes. So these areas are based on, I believe, ion count. So there's a lot of, it's times 10 to the 7. So they're pretty big numbers when the peaks get large. I'm just going to say, instead of using times 10 to the 7, I'm just going to use these numbers. So 1.791 and 3.507. So let's try to remember that. So let's say I want to figure out the percent area. That's what I'm trying to do here. Percent area of the bromide product. I'm going to look at the percent. So bromide is the 2.8 minute peak, and 3.507 is the area for that. So I'm going to take the area for this peak divided by the total area of both of the peaks together. So just take the area of one over the total area times 100. And this calculation has to be done because I just want to look at the relative percentages of just these two peaks. There could be other peaks showing, and I don't necessarily want to factor those in. So I just want to get these two. So this would be the calculation for that. So then you would do the same thing for the chloride, or you could just subtract from 100%. So 100 minus the percent of the other one. So that's fine as well. And then once you do that, you're going to make a table of, you're going to have your RCl and your RBR product. You're going to show the distribution as a percentage. So you can just enter those into a really simple table like this. And you can say starting alcohol, and you can draw the 3 different alcohols here that you started with. And then you could say what percentage of the chloride was here and the percentage of the bromide there from doing this calculation here. And then do that for all 3 alcohols. And then at the end, in your report, you should include a discussion of, why did the data turn out that way? Was it aligned with your prediction, or was it different? And what do you think accounts for that difference?